Hi everyone. We're moving on to Chapter 3, Applications of Derivatives. The first thing we're going to talk about derivatives being good for is figuring out how to do things in the best possible way. So lots of times when you want to do something the best way, what you really have is some sort of function, like a function for profit or cost or the light output by a light fixture or something, and you want that function to either be the biggest it can be or the smallest it can be. So maxes or mins. So often we want to maximize or minimize the value of a function. And when we're asking that question, what's the maximum or minimum, we're really asking two different but related questions. First of all, what is the maximum or minimum possible value this function can give me? And also, what should I do to get that maximum or minimum value? So which inputs into the function will give me the maximum or minimum output? Instead of saying maximum or minimum all the time, sometimes we lump those together and talk about the extreme values, or extrema of the function. Notice that the max or min value is a value of the function, f of x. So on a graph that would be the y value. And the input will be an x value on the graph. Okay, so before we start figuring out how to find the extreme values of a function, we have to figure out if they even exist. Do all functions even have extreme values, maximum or minimum values? So here's a few examples of functions. There's one. That is the highest y value on the graph, so it's the maximum value of the function. That's the lowest y value on the graph, so it's the minimum value of the function. So this guy has a maximum and a minimum. On the other hand, here's a function that has a minimum value, a lowest point on the graph, but because the graph continues up and to the right forever, there is no maximum value. There's also other situations where there's no maximum value, but this is just one example. So we don't always have to have a maximum value. And likewise, we don't have to have a minimum value either. This third function has no maximum and no minimum because it goes up forever and down forever. Okay, so no, not all functions have extreme values. Well then, is there a way we can tell if a given function does have extreme values? In general, it's a hard question, but there's one specific kind of function that will be guaranteed to have extreme values, and that kind of function is a continuous function on a closed interval. So if f is continuous on a closed interval from a to b, then f will definitely get to a maximum value f of c and a minimum value f of d for some numbers in that interval. Remember, a closed interval is an interval that contains its endpoints, so we use the square brackets. Okay, so the two main things we need are a continuous function on a closed interval, and if that's the case, we're guaranteed to have a maximum and we're guaranteed to have a minimum value somewhere in that interval. Okay, once we know we have extreme values, how do we find them? So, as a sort of first pass, we're going to look for local extreme values. Well, what's that? It's a place where the function gets as high as it can or as low as it can in that general vicinity. So there's the actual maximum value of this function, and there is no actual minimum value for this function. However, all these red dots indicate local maximum or local minimum values. The ones at the tops of hills are local maxima, and the ones at the bottom of valleys are local minima. A local maximum is a place where the function is the highest it gets in that vicinity. So a local maximum at c means f of x is smaller than f of c. F of c is the biggest if you only look at x values near c. Near is a shorthand way of saying in an open interval around c. So you only look in a little open interval around x equals c, then f of c is the biggest it can be. Similarly, a local minimum happens when if you only look in an open interval around c, f of c is the smallest it can be. visually on a graph, it's easy to find these local maxima occur sort of at the tops of hills usually, and local minima at the bottoms of valleys. One thing you may notice is that all of those that I've drawn here are places where the tangent line would be horizontal. And Fermat's theorem is a general statement. Local extreme values can only happen when the derivative is 0 or the derivative doesn't exist. Those are the only possibilities. Notice derivative equals 0 means the slope of the tangent line is 0, so that's a horizontal tangent line, like so. F prime doesn't exist means there's a corner or a discontinuity, or a vertical tangent line, but in that case you wouldn't have an extreme value. So what this says is if you're looking for local extreme values, you need to look for these kinds of places where the derivative is 0 or places where the derivative doesn't exist. Some of those places will give you local extreme values. Some of them won't. There's plenty of places where the derivative is 0 that's not a local extreme value, but these are the only places where they can possibly happen. So those are the places to look. Okay, so to look for extreme values of a function, first you find all the x values where the derivative is 0 or the derivative doesn't exist, like we just said. Those x values where the derivative is 0 or doesn't exist are called the critical numbers of the function. So we're looking for all the critical numbers of the function. After we find the critical numbers, we do some more stuff to look for extreme values of the function, and we will continue talking about this in class. But before then, here's a video question. I would like you to draw the graph of some function that has 2 local maxima, 1 local minimum, and no actual minimum, no absolute minimum. If the function you draw has an absolute maximum, mark it on the graph. If it doesn't, say it doesn't have an absolute maximum. But it should not have an absolute minimum, and it may or may not have an absolute maximum. All right, I'll see you in class.